Hi, my name is Colette Heald. It's my pleasure to present this poster, which describes some work which has really been led by my postdoc Cumming Fung, working with me at MIT. And the focus of this work is on exploring DMS oxidation and the implications of that chemistry for global aerosol radiative forcing. To motivate this work, I'd like to start with this figure on the left from the last IPCC. This figure summarizes the aerosol radiation interactions and the aerosol cloud interactions in green and the sum of the two in blue. And the symbols represent a number of different models and the bars are some averages shown here on the bottom. One important thing to note here is, of course, the large range and the estimate of aerosol cloud interactions or the aerosol indirect effect in the models populating this report. And you can see the values go from about negative half a watt per meter squared to negative 2.5 watts per meter squared. So quite a substantial uncertainty and range on these models. In addition, the satellite constraint has been estimated to result in a much reduced cooling compared to, let's say, some of the highest values of cooling estimated by models. So the expert judgment in the AR5 is that the aerosol cloud interactions are on average, the central estimate is about minus half a watt per meter squared. So there's somewhat of a discrepancy here between kind of these models, particularly those that are much more have much larger effects, much larger cooling effects from aerosol cloud interactions, and what is perceived to be the central estimate as reported by last IPCC. And one factor that may play an important role here is the pre-industrial aerosol burden. So to illustrate that, I'm showing here this figure from Ken Carslaw's paper showing how there is a nonlinear response between what's labeled here is the anthropogenic emissions and the cloud albedo. So effectively, the magnitude of aerosol cloud interactions is really highly sensitive to your starting condition. So in the case of having a very pristine pre-industrial, you will have a much larger response, for example, in cloud albedo, to the same increase in anthropogenic emissions compared to if that increase in anthropogenic emissions was added to a more polluted pre-industrial atmosphere. And so this motivates, developing a better understanding of aerosol formation in the pre-industrial. So one important source of natural aerosols is DMS. So dimethyl sulfide is emitted from the ocean, from phytoplankton, and in the atmosphere it oxidizes to form sulfate. So this is a key component of natural aerosol and prevalent through the marine environment. But that DMS chemistry has been really highly simplified in Earth system models, and it's neglected some pathways which might be relevant, particularly for clean marine conditions. And I'll note here especially the RO2 isomerization pathway, which I'll mention in a moment. So the goal of this work is to examine the impact of implementing a more detailed DMS oxidation mechanism into the CESM model, and then to explore what the impact is on the sulfate budget in pre-industrial and present day, and what, if any, impact this has on the aerosol indirect forcing estimate. So for this work, Cumming implemented this scheme into the CSM model, and this figure here summarizes what Cumming implemented. It's all based off of this series of references here, starting with this DMS here in green. So we have a number of different pathways in the gas phase. So we have oxidation by OH, BRO, and Cl leading to a suite of intermediates, ultimately getting you to the formation of sulfate. We also have other oxidation pathways, including NO3. And then in the aqueous phase, we have oxidation of DMS by ozone, which is a major pathway for formation of MSA. And then finally, we have the H abstraction pathway. This is primarily oxidation by OH, which forms the peroxy radical. So this is methyl-thiomethyl peroxy radicals, or MSP. And that MSP can go on to react with NO or RO2, as is sort of our typical fate of peroxy radicals in the atmosphere, and that will go on to produce MSA and SO2 and sulfuric acid. But that MSP can also undergo 2 consecutive hydrogen shifts, which leads to the formation of hydroperoxymethylthioformate, or HPMTF. And HPMTF is a key intermediate that was only recently confirmed in the atmosphere, and this was by Aerosol et al. In 2020. These are observations from the ATOM field campaign where they confirmed that HPMTF was widespread over the ocean. So there are a number of questions about the formation and the fate of HPMTF, but ultimately it's thought to regenerate the SO2, which is going to go on to form our sulfate. I don't have time to talk about some of those uncertainties in this poster presentation, but in our work we have explored the uncertainty of both the isomerization rates forming HPMTF and the loss processes, including a cloud uptake process that's been recently hypothesized, and looked at the budget and the impact that has on sulfate. And this connects as well to some work by my colleague, Jesse Kroll, whose group has been looking at the formation and fate of HPMTF, funded under this same project. Okay, so this slide describes the effect of this expanded DMS oxidation on the sulfur products and the DMS chemistry. So first here on the left, I'm showing all of the oxidation pathways for the DMS loss. So they're rank ordered here by the most dominant to the least important, going from OH via hydrogen abstraction, OH via addition, NO3, which you can see is dominant in the northern hemisphere where we have a lot of NOx sources, BRO, ozone in the aqueous phase, which is important in polar regions, and then some other minor contributors. It's important to note here that for the OH abstraction pathway, even in present day, most of this actually, over 90% of this, proceeds via the isomerization pathway. And so indeed, if you look at where does the DMS go, ultimately it sort of all makes its way to sulfate, but it gets there through these different pathways. And so about half of it goes via SO2, but a third of it goes via the HPMTF pathway, and the remaining goes through the MSA pathway. So it's clear that having these intermediates, are important and are certainly not negligible byproducts of the DMS oxidation. And by actually including sort of these intermediates that have a longer physical lifetime than sulfate, this chemistry actually increases the present day sulfur burden by about 8%. And so it has a significant effect, especially when you consider for present day, this 8% includes not only the natural sources of sulfurs from DMS, but also all the anthropogenic sources, right? They're sort of dwarfed by, the power plant emissions and so on and so forth. And so from a relative perspective, modifying the sulfur burden by 8% is fairly significant. We can then explore what the effect is of expanding this DMS chemistry on the sulfate that's formed. And so I'm showing you here the increase in sulfate observed in present day and in pre-industrial. So this is a column sulfate amount here. And you can see that there's about a 6% increase in present day sulfate, but an even larger impact on the pre-industrial sulfate, which increases by about 19%. And of course, in the pre-industrial, we have a much cleaner atmosphere, so that changes the relative branching and the relative oxidation by DMS, by different oxidants, and in particular, things like isomerization can become even more important. So what does this mean in terms of aerosol forcing? Well, I'm going to try and use this figure to summarize that. What I'm showing here is on the bottom is a standard here. So this is sort of our simplified chemistry, the pre-existing chemistry in the CESM model. And all of these figures show kind of a circle, a closed circle going to an open circle. That's 1850 to 2000. So you can see that if you compare that to our now modified chemistry, our increase, both of the endpoints here increase in our modified chemistry, but the increase in the pre-industrial is larger, right? Our starting point is larger. And so we do have this more polluted, and I say that in quotes because of course this is natural aerosol, but let's say a more aerosol-laden pre-industrial in our modified simulation. But the delta, the increase that you have in the sulfate from pre-industrial to present day, driven by anthropogenic emissions, is not very much affected by this condition, right? So we have a little bit of a dampening effect here, but these are, to all intents and purposes, largely similar. What is more noticeably impacted is the indirect effect. This is estimated here through the cloud radiative effect, and you can see here that the estimate of the aerosol cloud interactions, or the aerosol indirect forcing due to the rise of anthropogenic emissions from 1850 to 2000 in the standard CSM is about 2.2 watts per meter squared. However, implementing this modified chemistry and then the associated increase in the sulfate burden in pre-industrial dampens this indirect effect. And so we now get an indirect effect estimate of about 1.6 watts per meter squared. So that's about a 25% decrease in the amplitude of the aerosol indirect forcing. So this study confirms really that a detailed description of aerosol formation chemistry can really substantially impact pre-industrial aerosol levels, and thus the estimated aerosol indirect forcing. We found here that the detailed DMS oxidation chemistry translates to a 25% dampening of the aerosol indirect effect. And that comes at a cost of about a 15% increase in core hours using the Wyoming supercomputers. This is in CESM, of course. The improved description of aerosol formation under pristine conditions may therefore very well help close the gap between ESM estimates of the aerosol indirect effect and the observational constraints that were highlighted in the AR5. So we would like to gratefully acknowledge DOE support through the ASR program, and we are in the midst of putting this paper together. Accounting is working on a draft, and so we hope to have that submitted soon and look forward to any comments or questions you may have. Thank you.